So now that we have seen the algorithm BFS, and we showed how it works, and we argued that it is correct, we looked at the distances it computes, and they make sense. The question is, again, it takes us back to the question, is it efficient? We have seen brute force algorithm for computing distances. We analyzed its running time. It didn't look good. We said this is not feasible. Now we have come up with another algorithm that is all simple. The question, is it efficient? So now the next thing we need to do is to try to understand the efficiency of this algorithm. So we will look at this algorithm and try to analyze its running time and see how long it takes. As we showed before, is that when we have the algorithm, the first thing we should do is number the lines and start thinking about how long each line takes. Okay? And before we start analyzing the running time, we have to answer a few questions. Remember that we have now to talk about a specific implementation, and because we need to understand how these operations are going to be performed. So the first thing we are going to assume is that the graph is given by its adjacency list. Okay? The graph is going to be given by its adjacency list, not adjacency matrix. The second thing I'm going to assume, without loss of generality, that the graph that the algorithm is going to run on is going to be connected. Okay? The graph is going to be connected, which means there is a path from I, the initial node, to every other node in the graph. And the third thing we need to talk about is what is the input size. Okay? When we talk about adjacency list, it makes sense to think about the number of nodes and the number of edges. So I will assume that I have n nodes and m edges. Okay? So the number of nodes is n, the number of edges is m. Now that we know that the input size parameters are n and m, we know it is represented as an adjacency list. I assume it is connected. Let's see now how long it takes. Okay? So now the first line is initialize q to an empty q. This is, again, an individual operation, a basic operation that we will assume it takes on the order of one step. Okay? So I will say on the order of one step. Remember that O of 1 basically says that it takes a constant number of operations. For each node j in V, do something. How many nodes are in the graph? We assume that the number of nodes is n. Therefore, this is going to take on the order of n. Each time we are going to basically be doing just a simple assignment. This takes O of 1. Line 4 is just a simple assignment. It takes also a constant number of operations. In Q, Qi, adding an element to the Q is also a constant number of operations. It is one, or a constant amount, fixed amount of time. Now we come to this loop here. Now, how many times is this loop going to iterate? While Q is not empty, do the following. Now, if you think again about the illustration we showed, we had a graph with 6 nodes, and we illustrate this algorithm on it. If you go back and look at the illustration, you will notice, the first thing you will notice, that each and every node in the graph was added once to the queue. We started by putting node 0 into the queue, and then we put the neighbors of 0 in the queue, and then the neighbors of the neighbors, and so on. So if you think about the algorithm carefully, every node is going to be added to the queue. Remember, I made the assumption that the graph is connected, and this is where that assumption comes into the play and allows me to make that statement that every node is going to be added once to the queue. Because remember, if the graph is not connected, some nodes are not going to be added to the queue. But since I'm assuming the graph is connected, eventually, every node is going to be added to the queue, including the original node 0. Okay? So every node is added to the queue, and added once. So we know that the queue is going to have a size of at most n, or exactly n, actually, the number of nodes. Now the question is, in every iteration, what happens to that queue? In every iteration, the first line in that iteration is dq. So in every iteration, we are also going to remove a node from that queue. So the queue is going to have n elements added to it. In every iteration, one node is going to be removed from the queue. Okay? So if you think about these two statements, that every node is going to be added once, in every iteration, exactly one node is going to be removed. These two statements combined tell us that this loop is going to iterate n times. Okay? It's going to take n times. So this while loop here again, just to make sure you understand the concept, if we still have the first statement that every node is added exactly once onto the queue, but in some iterations, none of the elements on the queue are removed, then I cannot make this statement. Because if in certain iterations nothing is removed from the queue, then I will have more iterations. And if you don't have this line here, if you just look at the value of j without removing it from the queue, this actually will turn the algorithm into a non-terminating algorithm, okay? So again, you have to reason carefully about what's happening to the queue here to be able to understand how many times is this loop going to iterate. Every node is added exactly once. In every iteration, exactly one node is removed. Therefore, we have n iterations. How long does it take to remove an element from the queue and assign it to j? Again, it is a constant number of operations. For each neighbor h of j do. How many neighbors can j have? Okay. In the worst case, for some nodes, we might have n-1, at most n-1. Of course, when we are talking about an adjacency list, there is a given number of neighbors for every node. But again, as we said, we are not trying to get at the exact number of steps here. We are going to get an approximation. So I can approximate things and say, this loop, this line here, for a node j, I can have at most n-1 neighbors. Okay? In a graph that has n nodes, every node has at most n-1 neighbors. So this one here, I can say it's O of n. Okay? Because n-1 is O of n. This statement here, the if statement, is a simple condition to test. It's just a fixed amount of time. This is simple assignment here, is a fixed amount of time. The adding something to the queue is also fixed amount of time. The return is O of 1. Okay? So now that we have these numbers for every line, how long does this algorithm take? Okay? So we have O of 1 here. Then we have this loop here is going to take O of n. This line here is going to take O of 1. These two combined, they're going to take O of 1. Okay. Now we have this big one here. Okay. How long is it going to take? This is going to iterate n times, and in each iteration we are going to be doing also n times plus some constant. So we know now that this is going to be on the order of n squared. Okay. So these constants can go away, this constant, these constants, and so on. So it's order of n times order of n is going to be order of n squared. And this line here is just O of 1. So now I can just sum these numbers. I say it's O of 1 plus O of n plus O of 1 plus O of n squared plus O of n, O of 1. This is going to give me that the algorithm takes. Again, it's O of n plus n squared, but we focus on the dominating terms. N squared is a dominating one here. So using this analysis, we get that the algorithm is O of n squared. So this is our first attempt at analyzing the efficiency of this algorithm. And as you can see, this is a very efficient algorithm. It takes quadratic amount of time in the number of nodes in the graph. So like before, when we looked at brute force algorithm for computing distances, remember that even for 250 nodes or something like that, the algorithm would have taken 10 to the 59 years. If you have 250 nodes and it's gonna perform on the order of 250 squared, this is going to be done in fractions of a second on today's computers. Okay, so this is a very efficient algorithm, and this is using our first attempt at analyzing running time. We get an O of n squared time, so we can say that BFS takes a quadratic time in the number of nodes.